Good morning, professors. My name is VIET along with Du Nguyen, Thanh Trung, and Nhật Minh. We are from Vietnam, and today we would like to present a result from our study with the title Fabrication of Amorphous Microwire Materials Oriented to Biomedical Applications. Firstly, we introduce about our study. Magnetic refrigeration technology based on the magnetocaloric effect presents a promising alternative to the conventional gas compression technique. Owing to its high cooling efficiency and environmental friendliness, the MCE is a thermodynamic phenomenon in which the application of a magnetic field under adiabatic conditions causes a temperature change in the material. Many groups have been studied to improve the MCE in magnetic materials. The GD is a high saturation magnetization ferromagnet with its SOMT temperature at 294 Kelvin and large peak values of both delta SM and TAD, making it an excellent magnetocaloric material for sub-room temperature AMR. However, its high cost limits it from practical use. Contrary to bulk materials, the amount of material used in a cooling device based on thin films or ribbons or wires will allow their utilization in small-sized refrigeration systems. In addition, the wire shape is among the most favorable for the design of an AMR device, owing to the increased surface area to volume ratio that provides a high heat transfer between the magnetic refrigerant and surrounding heat transfer liquid. The main aim of our work is to study the fabrication of amorphous microwire materials oriented to biomedical applications.
Now, we briefly talk about experimental. The amorphous GD50, CO69.25, FE4.25, SI13, B13.5, 50 alloy microwires were fabricated by the melt extraction method. To obtain a uniform diameter for the melt extracted microwires, the high purity of the starting elements used to prepare the induction melted alloys. The structure of the wire samples was examined in the Braco D5005. DSC was studied on DSC lab system EVO. Energy dispersive X-ray spectroscopy and SCM were performed with a Geon SCM equipped with an INCA energy EDS system from Oxford Instruments. TEM was recorded on FEI, TEC, and AI G2F30 system.
Now we move to the main part of our presentation, results and discussion. The structural properties of the microwires have been characterized by XRD, EDS, SEM, TEM, and were shown in figures 1 and 2. From figure 1, we note that the XRD pattern of the microwires measured from 10 degree to 70 degree. Crystalline structure of these samples is amorphous. The amorphous characteristic of these microwires has been confirmed by the TM image. A typical EDS spectrum from SCM is also presented in figure 1b, confirming the presence of the raw chemical elements in the sample. As can be seen in figure 2a, the as-quenched hour microwires passes a smooth surface. The average diameter of the microwire was determined directly to be about 45 micrometers. Figure 3, the temperature dependence of the magnetization, left, and magnetic susceptibility, right, at H equal 10 millitesla. Inset shows the dm per tm versus temperature. The temperature dependence of the magnetization, MT for all specimens measured while cooling under a DC field of 10 millitesla. Clearly, the sample shows a paramagnetic to ferromagnetic phase transition at Tc about 172 K, defined as the inflection point of dm per tm versus temperature. The inverse susceptibility as a function of temperature, kappa minus 1 T, generated from the MT curves in the paramagnetic region, is also shown in this figure. Its linear temperature dependence is consistent with the Curie-Weiss law in the paramagnetic region.
In the figure 4, it shows the temperature dependence of magnetic entropy change into SM for different applied field changes. The magnetic transition becomes warrant with increasing applied magnetic field up to 5 Tesla. The largest changes in M respect to T occur around Tc. To evaluate the MCE of the microwires, we measure a set of isothermal magnetization curves mu0H at temperatures ranging from 30 to 262 Kelvin, with delta T equals 4 Kelvin at different field changes from 0.5 to 5 Tesla. Delta SM max was calculated to be around 5.9 joule per kilogram Kelvin at around 134 Kelvin. The figure 5 shows the LNM versus LM mu0H for temperature near the critical isotherm. The Tm is determined from the slope of the linear fit of the isotherm at 134 Kelvin. A log-log plot of field-dependent magnetization is shown in figure 5 at temperatures in the vicinity of Tc. The exponent delta can be determined from the inverse slope of the critical isotherm. A linear fit of the T equals 174 Kelvin isotherm results in delta fit equals 3.63, close to the value expected from the Witham relation of delta equals 3.678. The figure 6 shows the rescaling of the magnetization, the good linearity with beta equals 0.493, alpha equals 1.321, and Tc equals 174 Kelvin. We calculated delta equals 3.678 so that the three critical exponents obtained by the Colville-Fisher method are beta equals 0.493, alpha equals 1.321, and delta equals 3.678. From this figure, a good collapse of the Rees-Call magnetization is achieved, confirming the correctness of the critical exponents obtained from the Colville-Fisher method.
Finally, we conclude our research. We have investigated the structural, magnetic and magnetic caloric effect and critical exponent of GD50, CO69.25, iron 4.25, silic 13 and para 13.550 microwire. The microwire transform the paramagnetic to ferromagnetic transition around the Curie temperature 164 K. The magnetic entropy change has a maximum value delta SMS of about 6 joule kilogram K for a magnetic field strength of 5T. The Colville-Fisher method is used to analyze the critical behaviors of the PM2FM phase transition. A set of critical exponent value is found as beta equal 0.493, gamma equal 1.321, and delta equal 3.678. Thank you for listening.